In this video, we're going to learn about complex numbers, which allows us to take the square roots of negative numbers, something that we have not been able to do while working with just the real number system. So first, we're going to define what's called the imaginary number I. So our definition is that this number I is equal to the square root of -1. And so I squared is equal to -1. Now, I know that they call this an imaginary number, but that does not mean that it doesn't actually exist. Imaginary numbers and complex numbers are used all the time in real-world applications. There's, in fact, a lot of times that they're used in engineering, something that is very, very real. So don't get confused by it saying it's imaginary. That doesn't mean it doesn't exist. It's not just made up stuff. It's just the terminology that was chosen ages ago for this particular type of number. Now, if we have b as some number larger than 0, which is a real number, then we can do the square root of -b and write that as I times the square root of b. So now we have a way to actually calculate square roots of negative numbers. The negative would get pulled out of the square root as square root of -1, which is I. And then we still have the square root of b, which we can then simplify the way we normally do with real numbers. So let's do some practice simplifying some of these roots. So for an example, we're going to write the following things in terms of I. The first one is going to be the square root of -81. And until we were introduced to I, you would just say no real solution and be done with it. But now that we know about I, we can simplify this. We know the square root of -81 is going to be I times the square root of 81. Now the square root of 81 is 9. So I would write this as I times 9, or 9I is the way we would usually write that. And how about something like the square root of -50? Well, we know by definition, this is going to be I times the square root of 50. And then we would just have to try to simplify the square root of 50. It's not nice like 81. We can't just take the square root of it. We're just going to have to simplify it as much as we possibly can. My favorite way of doing that is I go on the side and do some scratch work, find two numbers that multiply to 50. So I'll just do 5 and 10. And then I can't break down 5 any further. It would just be 5 and 1. But I can break down 10 into 5 and 2. And now I have it completely broken down into numbers that can't be broken down any further. Since it's a square root, I look for pairs. I have a pair of 5s. That 5 gets to come outside of the square root. So I have a 5. I still have my I. And any numbers that didn't have a pair stay under the root. So I get 5I times the square root of 2 as my final answer. So now we're going to do a couple of examples multiplying or dividing some of these roots. So our instructions are to multiply or divide. And our first one is going to be a square root of -16 times the square root of -49. And you should try to simplify the roots first when doing this. So the square root of -16 we know is I times the square root of 16. And the square root of -49 would be I times the square root of 49. Now I can multiply the i's together. I times I is going to be I squared. Square root of 16 is 4. Square root of 49 is 7. I know 4 times 7 is 28. And I squared we know is negative 1. So I get negative 28. Let's do another example similar to this one. It's important when you have square roots of negatives that are being multiplied or divided that you try to simplify the roots first. Make sure you take care of all of those i's first, otherwise you may get an incorrect answer. So let's now do the square root of negative 48 divided by the square root of negative 3. And the first thing we're going to do is rewrite it without negatives under the root. So I'll have I times the square root of 48 over I times the square root of 3. And you see that the i's are going to cancel out. So I have square root 48 over square root 3. And now we just have to see, can we simplify this anymore? Square root of 3, if I tried to simplify that, well, 3 is just 3 times 1. I can't break it down, so I can't simplify that root. But 48, I can. If I find two things that multiply to 48, well, I think of 6 and 8. 6 is 3 and 2. 8 is a 2 and a 4. 4 is 2 and 2. So I've broken everything down all the way, and now I look at my pairs. I have a pair of 2's and another pair of 2's with a 3 left over. So that square root of 48, I have a 2 and another 2 coming out of the root, and that 3 that didn't have a pair stays underneath the root. And now I can see that my square root of 3's are going to cancel out, and all I have left is 2 times 2, which is 4. All right, so that is how we multiply and divide things involving negatives under a square root. Always simplify the roots first by taking care of those i's, and then you'll get to the right answer. The next definition for us, a number which is written in the form a plus bi, with a and b real numbers, is called a complex number. A is called the real part, and that B is the imaginary part because it's multiplied by that I. And just a reminder again that just because it's called imaginary doesn't mean it's actually just made up. It actually is a real thing. It's just not called a real number the way our other real numbers are. It's called imaginary. So let's simplify some expressions and write them in the form a plus bi, the standard form of a complex number. Simplify and write in the form a plus bi. So I have 16, I'm sorry, not 16, I was looking at a different example. 10 plus the square root of negative 75, all divided by 20. We are going to simplify this expression until it looks like a plus b times I. So the first thing I would do is I would rewrite this root so it has an I. So that's 10 plus I times the square root of 75 all over 20. And now I would split this into two different fractions. I have 10 over 20 plus I times the square root of 75 over 20. My 10 over 20 I can simplify to 1/2. And that square root of 75, we're going to need to simplify that. So let me do a little scratch work over here. 75 is 25 times 3, and 25 is 5 times 5. So I know the square root of 75 simplifies to 5 times the square root of 3. So simplifying my first fraction, I have a 1/2. Simplifying my square root of 75, I have 5 times the square root of 3. I still have a 20 in the denominator, and that's multiplied by my I. And now I just have to simplify that last fraction, and I will have this fully simplified and in the correct form. So I get a 1/2 plus a square root of 3 over 4 times I. All right. So now we're going to learn something pretty special about this number I, involving the powers of I. Let's just take a look at a lot of powers of I. If I have I to the first power, that's I. I to the second power, we know is -1. I to the third power is the same thing as I squared times I. So I know that's -1 times I, which is -I. And I to the fourth, that's the same thing as I squared times I squared, which would be -1 times -1, which is +1. Let's continue with some more powers. I to the fifth, well, that's the same thing as I to the fourth times I, which is 1 times I, which is I. I to the sixth, well, that's the same thing as I to the fourth times I squared. My I to the fourth was 1. My I squared was -1, so I get -1. I to the seventh is I to the fourth times I to the third. So that's going to be 1 times a -I, which is -I. And let's just do one more. I to the eighth would be I to the fourth times I to the fourth, which is 1 times 1, which is 1. So I notice I have a pattern here. I, -1, -I, 1. I, -1, -I, 1. And this pattern just keeps on repeating. The important things to notice is every single time we get a multiple of 4 as the power, we're back to 1. So we're going to be able to simplify really, really high powers of I by first rewriting it in terms of powers of 4. Every time you have a power of 4, it's just going to be 1. Let's do an example simplifying a really, really high power of I using what we just observed. We can simplify I to the 103rd power. And yes, if you really wanted to, you can just multiply I by I 103 times and you'll get to the same result. But I'm going to rewrite this using powers of 4 because I know I to the fourth is 1. So the first thing I'm going to do is think about that power of 103. I want the largest number I possibly can that is a multiple of 4, but still less than 103. And that would be 100. 100 is 4 times 25. So I can write I to the 103 as I to the fourth to the 25th, that's I to the 100th power, times I to the third. So just double check this real quick, make sure we still have the same thing. I to the fourth to the 25th, this guy is I to the 4 times 25, that's 100 power. I to the 100th times I to the third, you would add the exponents to get I to the 103. So this is the same expression. The only reason I wrote it this way is because I know I to the fourth is equal to 1. So I have 1 to the 25th, which is 1. And then I just have an I to the third, which remember I to the third is the same thing as I squared times I, which is -1 times I, which is negative I. So that is how you can simplify high powers of I. Try to find the highest power that is a multiple of 4, and then just simplify whatever's left. Now let's get some practice in adding and subtracting our complex numbers. So our first example, we're going to have the complex number 8 minus 3i minus the complex number 2 plus 4i plus the complex number 5 plus 7i. And even though I is not a variable, it's a number, you should kind of think of it like it is a variable when simplifying. You know, when you have a bunch of things with x's, we can combine our like terms that have the same x's in them. We're going to combine all of our numbers that don't have i's and combine all of our numbers that do have i's. So it's still combining like terms. First thing I'm going to do is rewrite this without all the parentheses. So I'll have 8 minus 3i. Make sure you subtract everything in the set of parentheses. So minus 2 minus 4i. And then I'm adding everything in the last set of parentheses, plus 5 and plus 7i. So let's take a look at just the numbers that don't have i's. I have 8 minus 2 and 5. 8 minus 2 is 6, plus 5 is 11. So I know I have 11. And now let's look at the numbers that have i's. Negative 3i, a negative 4i, positive 7i. Negative 3i minus 4i is negative 7i, and then adding a positive 7i to that would be 0i. So we could just write this as 11. All of the imaginary parts canceled out. This subtracted away the 0. Let's do another adding and subtracting problem, but introducing something that I know everybody enjoys. We're going to throw some fractions into this problem. So let's do the complex number 3/5 plus 5/6i minus the complex number 1/10 plus 1/3 I. So the first thing I'm going to do again is rewrite it without parentheses. So I'll have 3/5 plus 5/6i minus 1/10 minus 1/3 I. And now, just like the last problem, I'm going to have to combine the numbers that don't have i's and combine the numbers that do have i's. The only problem is I don't have common denominators. So let's first take a look what would I need to do to get the numbers without i's, 3/5 and negative 1/10. I need to have those with the same denominator. So I'm going to have to use a denominator of 10. To convert this guy into tenths, I would have to multiply by 2 over 2. So 3/5 is the same thing as 6/10. And then I have my minus 1/10. Let's look at our i's. I have 5/6i and a negative 1/3 I. So I'm going to have to turn this negative 1/3 I into 6 by multiplying by 2 over 2. So I'm going to have a positive 5/6i minus 2/6i. And now I can combine everything together because we have common denominators. So I have 6/10 minus 1/10. That's 5/10. So 5/10. And 5/6 minus 2/6i, we're going to have a minus 3/6i. And then these fractions can simplify. 5/10 is 1/2, and 3/6 is also 1/2. So I get 1/2 minus 1/2i. So when you're adding and subtracting complex numbers, remember to just combine the numbers that don't have i's and combine the numbers that do have i's. All of our other standard rules apply. You need common denominators when you have fractions, but then you just add and subtract like normal. Now, what if we need to multiply complex numbers? How would we do that? Well, let's see. Let's do an example where we multiply complex numbers. And we're going to write the result in the form a plus bi. And my problem is -5 plus 4i times 3 minus I. So just like with adding and subtracting, we're going to sort of think of the I as a variable, even though it's not a variable. So that means if you think about this with x's, we're going to distribute. And the same thing works with the i's. We're going to distribute everything to multiply this out. So I'm going to have -5 times +3. That's going to get me a -15. Then I have -5 times -i. That would be +5i. Now I move to the next part. I have 4i times 3. So that's going to be +12i. And then I have 4i times -i. And that's going to be -4i squared. And then we're going to simplify this some more. First things I notice is I can combine this 5i and that 12i together because they're like terms. And I know what I squared is. I squared is -1, so I can simplify that part over there too. So when I do that, we're going to have our -15. 5i plus 12i is 17i. And I said I squared is -1. -4 times -1 makes it +4. And now look at that. I have numbers without i's that can be combined together. -15 plus 4 is -11. So I get -11 plus 17i. And it's in the correct form, a plus bi. All right. So now we've done adding and subtracting and multiplying of complex numbers. The next logical step is, well, how do we divide complex numbers? And dividing complex numbers is a little strange. We have to use something called the complex conjugate. Let's define that. Definition. The complex numbers a plus bi and a minus bi are called complex conjugates. Notice that the only thing that's different between the two complex numbers is the plus or the minus sign. That sign in the middle changes. That's the only difference between the complex conjugates. These are going to be used to divide complex numbers. So to divide complex numbers, we're going to write them as a fraction. And then we're going to multiply the numerator and denominator by the complex conjugate of the denominator. So let's do an example seeing how this procedure works. So we're going to divide and write the result in the form A plus BI. And the problem I have to solve is 5 plus 6i divided by 2 minus 7i. And now the procedure that I need to use, I still have it written down. To divide our complex numbers, we need to multiply the numerator and denominator by the complex conjugate of the denominator. So I'm going to multiply this entire fraction by the complex conjugate of the denominator over itself. So the complex conjugate of 2 minus 7i is 2 plus 7i. And I'm going to put that on both the top and the bottom so that I'm not changing my problem. And now to actually multiply all of this out, we're going to have to do a lot of distribution. I'm going to put some parentheses around to emphasize that we need to distribute. And let's just start on the top. I have 5 times 2, that's 10. 5 times 7i, that's 35i. 6i times 2, that's 12i. And 6i times 7i is 42i squared. Do the same thing in the denominator. 2 times 2 is 4. 2 times 7i is 14i. A negative 7i times 2 is negative 14i. And negative 7i times positive 7i is negative 49i squared. Now take a look at this. In the denominator, my positive 14i and my negative 14i subtract to 0. That's exactly what's supposed to happen. When you multiply by the conjugate of the denominator, it should get rid of all of the i's in the denominator. Right now, yes, I still have an I squared right here, but we know I squared is negative 1, so we can simplify that. So what I have now, if I rewrite this, by combining like terms across the top and the bottom, and rewriting my I squareds as negative 1s, I'm going to have 10 plus, I have 47i, and plus 42 times a negative 1. And in the bottom, I have 4. My 14i and my negative 14i go away, and I have a minus 49 times a negative 1. So this, of course, is 10 plus 47i minus 42 over 4 plus 49. So now I can combine like terms across the top and bottom again. 10 minus 42 is negative 32. And I have plus 47i. All of this is over 53. And now to write this in the correct form, a plus bi, all I have to do is just split this up into two different fractions. I have negative 32 over 53 plus 47 over 53i. And that is our solution. So that's how you divide complex numbers. It doesn't even really feel like division. You multiply by the conjugate of the denominator on both the top and the bottom of the fraction. And that should get rid of all of the i's in the denominator so that you can split the result into the a plus bi form. That's all I have for this video on complex numbers. In our next video, we're going to solve some quadratic equations, and sometimes we're going to get complex numbers as the answers. So stay tuned for that. If you have any questions on these complex numbers, feel free to drop them down below. If you are my current student, you may email me or come to office hours to ask your questions as well, and I'd be more than happy to help. I'll see you next time.